What if I told you that 2 cubic inches, just 2, could completely dominate NASCAR's most elite racing series? That in 1987, a mechanic from South Carolina discovered a loophole so clever, so perfectly hidden, that it took NASCAR's best inspectors 2 full seasons to figure out what was happening? Picture this. It's Talladega Superspeedway, 1987. The green flag drops, and 35 of the most sophisticated racing machines on Earth thunder past at 200 miles per hour. But something's different about the Chevrolets coming out of one particular shop. They're pulling away on the straights. Not by much, maybe half a car length here, a car length there. But in NASCAR, that's the difference between winning and watching someone else spray champagne. The other teams are losing their minds. They're tearing down their engines after every race, searching for the secret. They check everything: camshafts, compression ratios, valve timing, fuel mixtures, nothing. According to every measurement NASCAR can take, these engines are legal 358 cubic inch small blocks, just like everyone else's, except they're not. This is the story of Robert Yates and the most ingenious cheating scandal in NASCAR history. A trick so simple yet so brilliant that it changed how NASCAR inspects engines forever. It's a story about finding power where nobody thought to look, about exploiting an accidental gift from Chevrolet's engineers, and about how sometimes the best place to hide something illegal is right in plain sight. To understand the genius of what Yates pulled off, we need to travel back to the mid-1980s NASCAR landscape. This was the era of the small block V8 arms race. Every team was running essentially the same engine, a 358 cubic inch pushrod V8, because that's what the rulebook demanded, not 357, not 359, exactly 358 cubic inches of displacement, measured by multiplying the bore area by the stroke by the number of cylinders. NASCAR inspectors would check this religiously. They'd measure the stroke of the crankshaft. They'd check the bore diameter at the top of the cylinder. Everything had to be within strict tolerances. The competition was brutal. We're talking about teams spending hundreds of thousands of dollars to find 5 extra horsepower. Engineers were experimenting with exotic cam profiles that would open valves for just a few thousandths of a second longer. They were hand-porting cylinder heads for weeks to improve airflow by 2%. They were mixing custom blends of racing fuel to squeeze out another 3 horsepower at 8,000 RPM. Richard Childress Racing, Hendrick Motorsports, Junior Johnson and Associates, these were multi-million-dollar operations with armies of engineers, and they were all hitting the same wall, with everyone limited to 358 cubic inches and similar technology. Engines were producing around 625 horsepower on a good day. Finding another 10 horsepower was considered a major breakthrough. Enter Robert Yates. Now, Yates wasn't some rookie wrench-turner. This was a man who'd been building racing engines since the 1960s. He'd worked with the legendary Holman Moody team, helped develop Ford's NASCAR program, and by 1987, he was the engine builder for Harry Ranier Racing, a top-tier NASCAR Winston Cup operation based in South Carolina. Yates had a reputation for meticulous attention to detail. Other engine builders would joke that Yates probably knew the weight of every valve spring to the 10th of a gram. But what set Yates apart wasn't just his precision. It was his ability to see opportunities where others saw limitations. The foundation of Yates's scheme was Chevrolet's bow-tie aluminum racing block. This wasn't your grandfather's cast-iron small block. The bow-tie block, officially designated as the Chevrolet Performance Parts PN 1051-3, was a purpose-built racing component. Cast from high-strength aluminum alloy, it featured priority main oiling, 4-bolt main bearing caps, and most importantly for our story, exceptionally thick cylinder walls. Chevrolet's engineers had designed these walls to be 0.4 inches thick, nearly twice as thick as a production block. The reasoning was durability. Racing engines operate at extreme temperatures and pressures. Cylinder walls flex and distort under these conditions. Thicker walls meant less distortion, better ring seal, and longer engine life. Chevy's engineers were particularly proud of this over-engineering. What they didn't realize was that they'd accidentally created the perfect tool for creative rule interpretation. Here's where Yates saw opportunity. NASCAR measured bore diameter at the top of the cylinder during inspection. They'd drop a bore gauge down, take a reading, do some quick math with the known stroke length, and confirm, yep, 358 cubic inches. But what if the cylinder wasn't the same diameter all the way down? What if it got slightly larger below where NASCAR measured? The standard bore diameter for a 358 cubic inch engine with a 3.48-inch stroke was 4.0 inches. That's what NASCAR expected to see. That's what they measured. But Yates realized the bow tie block's thick walls could handle being bored out to 4.060 inches, a full 0.060 inches oversize. That might not sound like much, but in an 8-cylinder engine, that extra bore diameter added up to 360 cubic inches of total displacement. 2 cubic inches doesn't sound like a game changer, but at 8,000 RPM, those 2 extra cubic inches were pumping additional air and fuel mixture 40 times per second per cylinder. The result? An extra 25 horsepower that nobody could detect. The execution required precision that bordered on art. Yates couldn't just bore the cylinders straight to 4.060 inches. NASCAR would catch that immediately. Instead, he developed a stepped bore process. The top inch of each cylinder maintained the legal 4.0-inch diameter. This is where NASCAR measured. Below that, Yates would carefully machine a subtle taper, gradually increasing the bore diameter as you went deeper into the block. By the time you reached the bottom of the cylinder, where the piston spent most of its travel during the power stroke, the bore was a full 4.060 inches. Think about the machining complexity here. We're talking about creating a precise taper over roughly 4 inches of cylinder depth, maintaining perfect cylindricity while changing diameter, and doing it identically 8 times. One cylinder slightly off, and the engine would vibrate itself apart. The piston rings had to be specially prepared to handle the diameter change without losing seal. The pistons themselves needed custom machining to match the larger bore at the bottom, while still fitting properly at the top. But Yates wasn't done innovating. He realized that with the larger bore area at the bottom of the cylinder, he could also modify the combustion chamber shape slightly. The extra bore diameter allowed for larger valves, not at the top where NASCAR might notice, but with modified seat angles that improved flow without changing the visible valve diameter. He was essentially creating a more efficient combustion chamber hidden inside the constraints of the rulebook. The machine shop work was performed in absolute secrecy. Yates trusted only 2 people with the actual boring operation, himself and his top machinist. The cylinder blocks were kept under lock and key when not being worked on. Even other members of the Rainier racing team didn't know exactly what made their engines special. They just knew Yates's power plants were rockets. The numbers tell the story. While other teams were struggling to get 625 horsepower from their legal 358s, Yates's hidden 360s were putting out a reliable 650 horsepower. 25 horsepower might not sound like much when you're talking about street cars, but in NASCAR, where races are won by hundredths of a second, it was enormous. At Talladega, where cars run wide open for entire laps, that extra power translated to about 2 miles per hour in terminal velocity. Over a 500-mile race, that advantage compounds into multiple second gaps. The first race where Yates's special engines showed their potential was the 1987 Winston 500 at Talladega. Davey Allison, driving the number 28 Texaco Havoline Ford, powered by one of Yates's motors, qualified third, but spent most of the race running up front. Other teams noticed, how was a relatively small operation like Rainier Racing suddenly running with the big boys? Harry Raniere himself played it cool, crediting improved aerodynamics and Davey's driving talent. But the real domination came in 1988. By now, Yates had perfected the overbore technique. He'd learned exactly how much taper he could get away with, optimized the piston and ring packages, and figured out complementary modifications that multiplied the advantage. The Raniere racing cars were untouchable on the superspeedways. Davey Allison won 2 races that season and finished in the top 5 14 times. Bobby Allison, Davey's father, also running Yates Power, won the Daytona 500. The competition was going insane, trying to figure out the secret. Richard Childress Racing completely redesigned their cylinder heads 3 times that season, convinced Yates had found some revolutionary port configuration. Hendrick Motorsports spent a fortune on exotic titanium valves and experimental cam profiles. Junior Johnson's team even hired a former Raniere racing mechanic hoping to steal secrets, but the mechanic genuinely didn't know about the overbore trick. NASCAR's inspectors were equally puzzled. After every race, they'd tear down the winning engines looking for violations. They checked displacement at the top of the bore, legal. They measured stroke, legal. They verified compression ratios, cam lift, valve sizes, all legal. They even started using more sophisticated tools like ultrasonic thickness gauges to check for acid dipping or other illegal lightning techniques. Nothing. As far as NASCAR could tell, these were perfectly legal 358 cubic inch engines that somehow made significantly more power than everyone else's perfectly legal 358 cubic inch engines. The breakthrough came from an unexpected source. In late 1988, a disgruntled former employee of a machine shop that had done some work for Raniere Racing reached out to a competing team with a tip: check the bore diameter at the bottom of the cylinder. That team quietly acquired a used Yates engine block from a crashed car and performed their own careful measurements. Their findings were explosive. The cylinders that measured 4.0 inches at the top were 4.060 inches at the bottom. But even with this knowledge, proving the violation was tricky. NASCAR's rulebook specifically stated how displacement should be measured, and by that method, the engines were legal. Yates had found a gray area, and he was exploiting it masterfully. The competing team faced a dilemma. Do they report it to NASCAR and eliminate the advantage, or do they copy the trick themselves? They chose option 3, build their own overboard engines while simultaneously tipping off NASCAR through back channels. By early 1989, at least 4 other teams were running stepped-bore engines. What had been Yates's secret advantage was becoming an arms race of who could hide the most displacement. NASCAR officials finally acted at the 1989 Daytona 500. New inspection procedures were announced. Bore diameter would now be checked at multiple depths using a special stepped gauge. Any variation beyond 0.05 inches from top to bottom would result in disqualification. They also introduced random teardowns, where engines would be completely disassembled and measured with coordinate measuring machines that could detect variations of less than 0.031 inches. The first casualty of the new rules was, ironically, not a Yates engine, but one from a team that had tried to copy his technique without his precision. They'd overbored their cylinders, but hadn't managed the smooth taper Yates achieved. NASCAR found a 0.015-inch step in their bore, clear evidence of intentional cheating. The team was fined $50,000 and suspended for 4 races. Yates, ever the professional, simply smiled when asked about the new inspection procedures. NASCAR makes the rules, we follow them, he said. We'll build the best legal engines we can within whatever framework they establish. Behind closed doors, though, Yates was already working on his next innovation. If he couldn't hide displacement in bore diameter, maybe he could find it somewhere else. The immediate impact of the overbore scandal was a complete overhaul of NASCAR's inspection process. The sanctioning body invested in new measurement equipment, hired additional inspectors with engineering backgrounds, and established a policy of sealing engines after inspection to prevent post-inspection modifications. The cost of policing the sport increased by an estimated $2 million per year, all because one clever mechanic found 2 cubic inches where nobody thought to look. But the real revolution was in how teams approached engine development. Yates had proven that tiny advantages, properly hidden, could dominate the sport. The era of creative interpretation had begun. Teams hired lawyers to parse the rulebook for loopholes. Engineers started thinking not just about what would make power, but what would make undetectable power. The psychological warfare intensified. Teams would deliberately fail inspection with obvious violations to distract from their real tricks. The technical legacy of the overbore trick extends beyond just displacement games. Yates's stepped bore concept actually had some genuine engineering merit. The larger bore at the bottom of the cylinder, where combustion pressure was highest, provided more surface area for force transmission to the piston. The smaller bore at the top reduced crevice volumes where unburned fuel could hide. In a weird way, Yates had accidentally invented a more thermodynamically efficient cylinder design while trying to cheat. Modern NASCAR engines, now restricted to exact specifications with zero tolerance for creativity, produce over 850 horsepower from the same 358 cubic inches. How? Through exactly the kind of development Yates pioneered, finding power in places nobody else was looking. Today's engines use exotic materials, precise fuel injection, and computational fluid dynamics to optimize every aspect of combustion. But the philosophy that racing is as much about outsmarting the competition as outrunning them, that comes straight from Robert Yates' playbook. The bow tie block itself became legendary. Chevrolet discontinued it in 1991, partly because the thick cylinder walls that enabled Yates' trick were no longer necessary with improved metallurgy, but original bow tie blocks became collector's items. Racing engine builders would pay premium prices for new old stock blocks, not because they planned to overbore them, but because owning one was like owning a piece of NASCAR history. Yates himself went on to become one of NASCAR's most successful engine builders and eventually a team owner. Robert Yates Racing won multiple championships and dozens of races through the 1990s and 2000s. But among the engine-building fraternity, he's still remembered primarily for those 2 extra cubic inches. It wasn't his most sophisticated innovation or his most powerful engine, but it was his most audacious. He'd beaten NASCAR at its own game, using nothing more than clever machining and the accidental generosity of Chevrolet's engineers. The human side of this story is equally fascinating. Robert Yates wasn't some villain trying to destroy the integrity of racing. He was a competitor doing what competitors do, finding every possible advantage within his interpretation of the rules. In interviews years later, Yates would neither confirm nor deny the specifics of the overbore trick, but he'd always smile when asked about it. Racing is about going fast, he'd say. Sometimes that means building better engines. Sometimes it means reading the rulebook more carefully than the other guys. The drivers who benefited from Yates's engines had mixed feelings when the truth came out. Davey Allison, who'd won races with the overboard engines, insisted his success came from talent, not trickery. 25 horsepower doesn't drive the car, he said. It doesn't make the right decisions in traffic or nail the setup. But privately, drivers admitted that in a sport where everything matters, those extra ponies were the difference between running up front and running in the pack. The other engine builders, once they got over their initial anger, actually developed respect for what Yates had accomplished. It took genuine engineering skill to execute the stepped bore properly. It took creativity to see the opportunity in the first place. And it took serious courage to risk everything on such a bold interpretation of the rules. We were all trying to cheat, one rival engine builder admitted years later. Yates just did it better. NASCAR itself learned valuable lessons from the overbore scandal. They realized that as technology advanced, their inspection procedures needed to advance as well. They established technical partnerships with engineering universities to stay ahead of creative cheaters. They implemented whistleblower programs to encourage insiders to report violations. Most importantly, they recognized that the battle between regulators and innovators was part of what made the sport exciting. The philosophical implications of Yates's trick resonate beyond racing. In any competitive environment with rules, there will be those who follow the letter of the law and those who follow the spirit. Yates demonstrated that sometimes the biggest advantages come from questioning assumptions. Everyone assumed cylinder bores had to be straight because that's how they'd always been made. Yates asked, what if they weren't, and changed the sport forever. The overbore scandal also highlighted the importance of precision in modern competition. 2 cubic inches, a 0.56% increase in displacement, was enough to dominate NASCAR's Premier Series. In today's world of marginal gains, where Olympic races are decided by thousandths of a second and Formula One championships by tenths, Yates's trick seems almost quaint. But in 1987, it was revolutionary. It showed that in professional sports, there's no such thing as an insignificant advantage. Looking at modern motorsports, the spirit of Robert Yates lives on in every cleverly interpreted regulation, every creative solution that walks the line between legal and illegal. Formula One's dual-axis steering systems, NASCAR's manipulated body panels, MotoGP's aerodynamic winglets, they're all descendants of Yates's stepped bores. The game continues, just with different rules and more sophisticated referees. The technical specifications of those illegal engines remain impressive even by today's standards. The 360 cubic inch displacement was achieved through a 4.060-inch bore and 3.48-inch stroke. Compression ratio was kept at a legal 12.1 to avoid suspicion. The engines used a flat tappet camshaft with around 650-inch lift and 286 degrees of duration at 0.052-inch lift. Valve sizes were 2.08-inch intake and 1.60-inch exhaust. With the improved breathing from the larger displacement and optimized combustion chamber, these engines produced peak power at 7,800 RPM and could rev safely to 8,500 RPM. The cost of developing and maintaining these engines was astronomical. Each stepped bore block required about 40 hours of precision machine work. The special pistons and rings cost 3 times as much as standard components. Yates estimated that each engine cost about $75,000 to build in 1987 dollars, roughly $190,000 today. But when race wins paid $100,000 and championships were worth millions in sponsorship, it was a worthwhile investment. The machine shop where Yates performed his magic became something of a shrine after the story broke. The specific boring machine, a Sunnon SV10 honing system, was kept in service long after more modern equipment became available. Yates said it was because he knew exactly how that machine behaved, but others suspected sentimentality. That machine had changed NASCAR history. Today's NASCAR engines are marvels of engineering that would astound the racers of 1987. But they're also more restricted, more regulated, more homogeneous. The era of finding 2 secret cubic inches is over. Electronic sensors monitor every aspect of engine performance. Sealed components prevent modification. Spec parts ensure equality. In many ways, the sport is fairer. But something was lost when characters like Robert Yates could no longer outsmart the system with nothing but creativity and a boring bar. The legacy of the overbore scandal isn't just about cheating or clever engineering. It's about the perpetual dance between innovation and regulation, between those who push boundaries and those who enforce them. It's about how competition drives creativity, sometimes in unexpected directions. And it's about how one man from South Carolina proved that in racing, as in life, The biggest advantages often come from seeing what everyone else overlooks. Robert Yates passed away in 2017, but his influence on NASCAR remains profound. The engines that power today's Cup Series cars, though vastly different in design, still chase the same goal Yates pursued, finding speed wherever it might hide. The difference is that now everyone's looking in the same places he taught them to look. The stepped bore trick wasn't just about 2 cubic inches. It was about changing how racers think about rules, innovation, and the pursuit of speed. What's the most creative interpretation of rules you've ever seen in motorsports? Share your thoughts below, and don't forget to subscribe for more stories of engineering brilliance that push the boundaries of what's legal, what's possible, and what's fast.